Hi, everyone, and welcome to this month's installment of Teaching Space with NASA. My name is Brandon Rodriguez. I work in the Education Department at NASA's Jet Propulsion Laboratory. Very excited to have you guys back. If you've joined us before, and if this is your first time, thanks a lot for tuning in. What we'll be talking about today is the Deep Space Network, which I'm very, very excited about our speaker, Bernardo Lopez, who's going to run us through a little bit about how it is we communicate with our spacecraft across the solar system. Before we turn it over to him, I wanted to highlight just a couple things. First and foremost, it's the apocalypse, and California is on fire. So as a result, normally we have some studio support. We're able to go into the lab and work from there. Unfortunately, because of the fact that we can't get access to the laboratory, we're effectively running this off our personal Wi-Fi's today. So we didn't want to cancel on you guys and really wanted to make sure that this event still happened. So we've got our miracle worker, Lyle Tavernier, effectively building a TV studio in his home. And I hope that you guys will bear with us if there are any technical or audio issues as we move forward. Another really important thing to cover is that this is, I believe, the fourth installment of this. And in the past, we've really focused on Mars and the Perseverance rover. And that's because leading up to the launch, this was really a critical focus. But it's important to note that Mars is, while an important piece, really a very small piece of everything that JPL does. So to that end, it's really important that we finally focus a little bit more on the infrastructure, the engineering that allows for all of these space missions to take place. And to that, I think we'll really enjoy exploring some of these future research missions to allow us to even further expand how it is we do what we do at NASA. As usual, we'll have our guest speaker run us through some slides and give us a little bit of a technical perspective. We'll do about 10 or 15 minutes of Q&A. I hope you guys registered. You still can for the live stream questions. If you're just watching, absolutely fine. We're happy to have you here. But if you'd like to have your questions answered, you want to make sure you register on the Teaching Space website. At the end of that, we'll cover a little bit of education slides and some resources so that you can take this lesson to your students or to your kids at home to kind of further develop some of the material that we covered today. So with that being said, let me please turn it over to Bernardo Lopez, and thank you so much for joining us today.
Hello, everyone. As you've heard today, I will talk to you about NASA's Deep Space Network, which is the project I work on. So the Deep Space Network, let's see. So to get started, perhaps you have been amazed at the pictures of views of dust storms or dust devils forming on the surface of Mars, or the amazing close-up pictures of the planets taken by spacecraft like Voyager, Galileo, Cassini, and many others. And who can forget the surprising and awe-striking finding of geysers on Saturn's moon Enceladus by Cassini in 2015, or the sharp images of the antennae galaxies in the group we call NGC 3048, sent to us by Hubble telescope and many others. Well, all those images, as did the voices of astronauts from the Apollo missions during our visits to the moon, have come to us through the Deep Space Network antennas. Those antennas make up NASA's DSN. You know, today, you can just pick up your cell phone and call your grandparents or your parents, send a text message to your friends, or connect via Skype or WebEx, etc., to one of your classes. Well, NASA has a way to connect with the many spacecraft we send to explore our solar system and the universe. As you may have guessed by now, that is through our Deep Space Network antennas. So what is the Deep Space Network? It is the messaging, the communication link, the connection between Earth and our exploration spacecraft in deep space. It is a team of radio telescopes or antennas located at 3 stations around the world. You may ask yourself, what is deep space? Well, deep space is a distance far enough from Earth such that our spacecraft will always be in view of one of our antenna stations. Another definition is a distance of 2 million kilometers from Earth. Either way, that is very, very far away. So, what type of information do we communicate or exchange with our spacecraft? Well, from them, we receive science data, observations like photos, data files, or voice at the time of the Apollo missions, experiment results, spacecraft health information, instruments, diagnostics, fault error, or fault or just error messages. And very important, the location and navigation information of the spacecraft so that we always know where they are and where to point our antennas to so that we can talk to them. So from us to them, we send commands for tests and diagnostics, navigation corrections, task preparation, task changes, instrument activation and activity commands, or requests for diagnostics, and sometimes even reprogramming of one of their computer systems if necessary. We go to slide 8, we can see that in the DSN, we have 2 basic antenna sizes. One with a main reflector of 70 meters in diameter, which weighs some 9 million pounds above its supporting concrete pedestal. And the others are 34 meters in diameter, and for these we have 2 designs. The older one, which we call the high efficiency antenna, and the newer design known as the beam waveguide antenna. And these weigh approximately a bit less than 1 million pounds each. We have 170-meter antenna per station, and also a HEF, which we are slowly retiring from service nowadays, and 2 to 3 beam waveguide antennas per station. On slide 9, you will see that, as I said, the DSN has 3 stations around the world. One is in Robledo de Chavela, about 35 minutes out from Madrid, the capital city of Spain. One in Goldstone in the Mojave Desert, some 30 minutes north of Barstow here in California, and one some 35 minutes from Australia's capital, the city of Canberra, in the area of Tinbinbilla. So each of the stations is located at 120 degrees apart from the other so that we can give full coverage of the 360-degree circumference of the entire view of the universe. Go to slide 10. So how do we talk to our spacecraft? We use antennas here on Earth, and we also use antennas on the spacecraft so that we can talk to them. We use a type of light to communicate with our spacecraft. That light has a frequency we call radio frequency for short, but it's actually somewhere between radio and microwave. And that light through our atmosphere as well as through space. The antennas use a lot of advanced methods and equipment to make sure that we stay connected and communicate using the best signal possible. Going to slide 12. Actually, I'm getting ahead of myself. Let's go to slide 11 here. And although our DSN antennas were designed decades ago and continue functioning very well today, Due to the future demands for higher amounts of data going through them, especially with missions putting humans back on the moon and on Mars, we are currently working on the design of an optical antenna that will have various frequencies to use, and each will be transferring much larger volumes of data than today. With human missions, you see, knowing the health of our astronauts and monitoring their progress will be extremely important, in addition to our science goals and spacecraft conditions. So the optical reflector, as you can see on the left side of the view here, is nestled in the center portion of the beam waveguide antenna. So we will actually have two antennas in one, a radio frequency and an optical antenna. Now, going to slide 12, the DSN antennas need a lot of tender care. They are, yes, in top condition and functioning very well today, but that is thanks to the large team of engineers and scientists that we have both at JPL and at each of the three stations, working hard every day to maintain, monitor, repair, and modify our current antennas so that they are always ready to work for us, communicating with our spacecraft on time and for the duration necessary. Now, if we go to slide 13, currently we have dozens of missions that we track every day, and we are always communicating with one spacecraft or another. And you yourself can actually go to the EYES DSN and look for your look at that yourself. And on the left side, you will see our three stations and what antennas are working. There will be some that are grayed out and some that will show lit up. Those are ready and operational today. The others are maybe under maintenance. And among those, you will see some transmitting data. And on the right, you'll be able to see, you can click on the antenna that is transmitting data, and on the right, you will see a view of that antenna and the name of the spacecraft they are communicating with, how far away that is, and the round trip distance of the signal. So enjoy and stay connected yourself by looking at what DSN is doing for our spacecrafts, our missions, and all our customers worldwide. So this is the end of my presentation to you, and we'll move on with some questions.
Awesome. Thanks so much, Bernardo. I really like that you highlighted the DSN EYES component, because that's the view that we have in spaceflight operations, JPL's mission control. So it's really like you guys are getting to see exactly what we see when we're on lab. You have a ton of questions here. You drew quite a crowd, from a pretty impressive sounding geoengineer in Sacramento to high school students in India. So we'll tackle the top ones first. Looking at the current state of DSN, as well as moving to this optical DSOC, what are the frequency bands that spacecraft use, and what powers these communication systems right now?
Yes, so we use a variety of frequencies, and that has evolved over time. These frequencies are assigned like short names like S band, X band, KA, and so on. And so the frequencies range anywhere between 1.5 gigahertz to about 34 gigahertz. All right, and but when we are in the optical mode in the future, that will be much higher frequency, and the frequency determines how much data you can put through. And so the power that we use, our transmitters are anywhere between 20 to 100 kilowatt, 80 kilowatt, 20 to 80 kilowatt. So that's a lot of power.
Yeah, it brings up an interesting point, which is obviously when it comes to data limitations, we can't change the speed of light. So what is it, if you don't mind getting into kind of some of the basic physics for our audience here, why is it that changing the frequency allows us to get more data?
Well, so the frequency, if you think about, those of you who play music, there's such a thing as beat, right? How many beats you get per second or in a given amount of time. So the communication frequency is similar to that. All right. So, for example, just with the current frequencies, if we transmit at 1.5 gigahertz, but then we have the capability to transmit at 15 gigahertz, that's 10 times more information that we can fit in 1 second in any given amount of time. So if we go to optical, that is orders of magnitude higher. So we will, multiply the amount of data that we can get through.
Yeah, and maybe that segues nicely into why is it that you're exploring DSOC? So what is the current state of the DSN as is? Why not just build more antenna? Why switch to optical in the first place?
So if we build more antennas, that is like putting a larger telescope in front of our eyes or a larger set of binoculars. But we will still be seeing the same frequencies, okay, or the same amount of data. It's just that, we can see it bigger and better, but the amount of data that's coming to us is still the same. So that is why we need to increase the frequency, not only because then we increase the amount of data coming through at any one frequency, but then if we are in the optical area, think of all the colors that our eyes can see. So that's the optical regime. And so we can see anywhere between red to violet, for example. So each one of those frequencies is like a different channel that we can tune into. So while today we have, say 3 main channels, in the future we can have more channels.
So I guess it begs the question, why stop there? So why just visible light? Why not infrared?
Well, one of the challenges, for example, infrared is like lower frequency, right? And so we perhaps don't want to go to infrared, but let's go to ultraviolet, for example, or even higher frequencies. Some of the challenges that we have, let's think of ultraviolet, for example. Well, we know that a lot of the ultraviolet radiation that comes from space, predominantly the sun, gets blocked by the ozone layer, for example. So the atmosphere, while it protects us, can play against us. For example, when we are in the optical regime, we know that clouds will become an obstruction to that communication. So we'll be able to communicate when the sky is clear. So that will be something that we'll have to play with real time when we are scheduling the communications, but we will also have the other frequencies as backup.
Gotcha. A really good question coming in here is, what is the effective maximum distance that we can communicate both presently and perhaps if we were to implement something like DSOC? And then maybe a bit of a follow-up too. What are the hurdles for DSOC? Why, if it is so much better and we can get so much more data, why aren't we doing it?
Yeah. So Why haven't we been doing what we project to do in the future? Part of the reason is the need was not quite there. We were able to manage with the technology that we had, but also every time you advance in the capabilities, you're also talking about developing new technologies. Um, Putting in an optical portion to the radio frequency antennas is a challenging, very challenging proposition. So while we are working today to design that, that it will be years into the future before we implement it, but we have to do so in time for when these human missions get executed. Now, in terms of the limitation for the distance that we can cover, an example of where our reach is today, the farthest spacecraft we are tracking are the Voyager mission spacecraft that left Earth some, if I'm counting correctly, some 33 or maybe 43 years ago. And the farthest one is a bit more than 21 billion kilometers away. So that is a very, very far distance. And so what happens is, as you go farther in distance, the power, if you will, of that signal becomes smaller and smaller and smaller because our antennas have just so much aperture, if you will, and so much power in transmission. And the size of the antennas on those spacecraft is already set. So the farther away the spacecraft are, is like we talking to someone in the next room, but if they start walking away across the street and we're talking with the same level of voice, then it is a lot harder to hear. So those are the physical limitations, right, that we have to deal with.
Kind of going to the idea of the Voyager, how is it that we actually keep track? What's happening astrometrically, really, to be able to keep an eye on spacecraft so far away and be able to, get data across these great distances? What does that control and tracking and guidance look like?
How about now? Sorry about that. So the signals have a very specific coding that we look for. It's like we call that a carrier signal. So we know when we're tuned to that spacecraft, right? And so we know where the spacecraft is supposed to be and where it will be, say, 9 hours from now when we want to latch on to one of them. So we point our antennas to that position and we send a signal. And then we get the signal back, acknowledging that we have a connection, and then we start communicating. And the data is really coded, like I said, a bit, to a certain extent, so that we know within that whole package of information what is diagnostics or health of the spacecraft and what is science. So part of our team of engineers at JPL, their job is to decode, and sort out, out of all that data, what are navigation or the health of the spacecraft from the actual science. So that is something we have lots of experience with for decades. And it's a true and tried method that we'll keep on relying on to be able to communicate.
I have a question here that I know a lot of us were asking, actually, was if you recall during the latest SpaceX launch to the ISS, there was a moment where it looked like connection was lost, and the statement was that this is kind of normal because of perhaps that distance effect you measured in terms of what's local versus what's deep space. Can you elaborate on how that took place and what happened there?
Um, yeah, Brandon, and for everyone, unfortunately, I don't have the details as to what happened, but I can, in order to illustrate how difficult going to space is, let's think of the fact that the environment of our in on Earth and inside our atmosphere is a certain type of environment. But the further we get away from the surface, the environment starts changing. Not only that our atmosphere is getting thinner, which is actually helpful for the communications, but what's happening, we enter into an area with higher temperatures and then a lot more particles, charged particles, as we go into the magnetosphere. So we have two main layers of protection around our planet. One is the atmosphere, and the other one is the magnetosphere. And the magnetosphere actually protects our planet from the constant rain, if you will, and storms of particles that come from the sun. So it is often that the Earth gets bombarded by some solar wind and flux of higher strength that can actually um, wreak havoc with our telecommunications. So from time to time, we have to think about protecting our spacecraft from those events. So outside of the magnetosphere, there's a lot going on that can actually cause damage to our telecommunications, but also to the health of the spacecraft. So, you know, those are considerations that we're always dealing with when we have to communicate with our spacecraft. And of course, some of these things could also happen during launch or orbit transfer.
Um, Kind of in a similar vein, there's a question here that seems kind of the natural next one to ask, which is beyond protecting the satellites or our spacecraft from natural environments, what about protection from like cyber threats in this day and age? How are they protected?
Yeah, so our spacecraft have their own computer systems, right? And also they have their own software operating systems. And while I'm not a software engineer, I can assure you that in the process of developing this software, which we do in our computer systems, JPL or elsewhere, we have to protect that development so that we don't get any bugs or threats coming into the spacecraft. Just like you said, just like we protect them from contamination and from foreign objects, and we put thermal blankets on them to protect them from high or low temperatures, we also have measures that protect them from viruses in the software to so that we have a healthy computer system as well.
Maybe the last technical question I'll ask you then is, you know, are there redundancies in place? How do we, kind of as an engineer, how is it that we kind of keep everything up and running through, right now through whether it's fires or earthquakes? So, how do we make sure that business is running as usual?
Right. So um, fall detection or single catastrophic events for any one mission is something that's always present in our minds. When we start designing a mission, that is always there. In the conceptual design through all the maturation phases, we're always asking whether something is a critical requirement. For example, okay, the spacecraft has to be able to communicate with our antennas, for example, at such and such frequency. Well, what if the transmitter, uh, uh, um, has a glitch? What is our plan B, if you will? Okay, for the DSN, our plan B is we have another antenna standing by if it is a critical event. If it is, say, we're going to start landing, we're going to be landing on Mars, and we're waiting to hear from the rover to say, I'm here, I'm healthy, I made it, I made it home. And so we always have another antenna standing by, either at the same complex or maybe at another station that can see Mars from that location of the Earth. So we're always having a plan B. And that is part of the way we operate, either on the ground or with our spacecraft. And that is key to our success.
Perfect, perfect, perfect. Um, I I want to kind of transition a little bit to you. You have a multitude of questions, a little bit about your journey to NASA. We have a huge international audience with us today. So a lot of people are wondering, how did you get here? What did school look like? What degrees did you pursue? And what got you to NASA in the first place?
Yeah, good. Thanks for that question. It's very important. It's interesting. I was actually born in the country of El Salvador. And as a little kid there, I didn't know exactly what I wanted to do. First of all, I thought, well, university is probably going to be very expensive. I don't know whether I'll be able to study the kind of career I would like. Um, and I remember reading an article when I was 12 years old that talked about a comet, the code tech, and scientists at JPL that were tracking it and studying it. And I thought it would be nice if I could work there at some point. Well, you never know what opportunities life will offer you. And so, keep on studying, right? And that's what I did. And later, I found the opportunity. Well, I came to the United States when I was 18, and I enrolled in the university to study sciences and math. Very important to be an engineer, a scientist, and later I realized that I wanted to be in aerospace. So I went to school for aeronautical engineering, which is the design of aircraft, but also spacecraft, rockets, and the likes. And I was a good student. I was fortunate that way. And I got a scholarship from a company called TRW Space and Electronics. Now it's north of Grumman here in the Los Angeles area, which guaranteed that I would have a job when I graduated. And I started working there, doing structural engineering, doing analysis to make sure that during launch would not fall apart, because that's a very shaky event. And at the time, then I was contacted by someone at JPL who wanted to do some research on new types of structures. And I decided to come to JPL. Later, I realized that, my goodness, this is really where I wanted to be when I was 12 years old. So the message here is don't put limitations on yourself. Always be ready for the opportunities. Study hard, identify a goal and keep your eyes on that goal. Stay on that course, and you will eventually get there. And then later you will realize that the opportunities will show up, okay? And you will be surprised as to where you are. And I have to tell you, for many of us, if not most of us at JPL and at NASA, I can say we feel privileged and humbled, really, to be able to do this, not just for the United States, but also for humanity. And many times work is very challenging and very hard, but this is something we cannot ignore. Exploring space, that is our frontier. That's where the future is. And So we're committed to doing it, and we need many of you students out there to stay steady. And one of these days, you will be doing this kind of work. We have many generations that hopefully will continue this journey.
Yeah, yeah. Thank you so much for that. It's so perfectly put. I know that you work with students a lot, and when I speak to students, I try to convey to them that even though I think baseball is the worst sport in the world, that really one of the valuable lessons it teaches is that there is incredible value to just getting on base. You don't hit a home run every time. None of us just kind of fell into NASA or JPL. We worked and worked and worked, and it kind of just got closer every time. So I think it's a really great message. I appreciate you sharing.
Brandon, I want to highlight one thing. Teamwork is very important, and it is a key component of what we do. We work in teams at JPL, but as you all know, working in teams brings the best of different people, and we cannot achieve difficult things alone. So start exercising your abilities to work in a team, because that is key to the success.
Perfectly put. Well, with that, we'll let you go. Thank you so much for joining us today. Really appreciate it, and I think you've really given us a great outline for the Deep Space Network and future research. So thank you so much.
It's my pleasure. Thank you all.
So what I'd like to do now is just transition to just a couple quick slides on some of the resources that we have at NASA Education. That way, again, if you really enjoyed what you heard today, or you have more questions, maybe I can point you to the right place to learn a little bit more. On slide 1 of my presentation here, you'll see just a screenshot of the NASA Education website. And you can see, due to everything that's going on right now in the California and the West Coast, we have some interesting updates on the science of wildfires. But you'll also notice at the top there's several options for you guys to peruse through. Things like our teach section, which are a little bit more highlighted for teachers. So if you're leading a classroom, versus a learn section, which is a little bit more self-guided. In this, whichever section you go to, you're going to find a ton of resources and activities, like you'll see on slide 2. One example of this is what we call the solar system scroll. This is kind of predicting and mapping out the relative distance in between all of the planets in our solar system. So for you that were asking, how long does it take to communicate with one planet versus another, this will give you a little bit of perspective of just how difficult that truly is. For example, Mars being our nearest neighbor, that's a quick call. But as you'll discover if you do the activity, our planets are not evenly arranged, not evenly spaced out through the solar system. So some of these are really much further than others. Another activity on slide 3 is this modeling the Earth-Moon system. And this is a great activity just for fun or with young kids. A subsection of it is just taking balloons and looking at like the relative size of the Earth versus, as well as the distance in between them, using a little bit of math. We're always here to trick you into using a little bit of math. On slide 4, I want to point out that we have not just individual lessons, but actual like unit plans built for, again, a classroom instruction setting. So if you are wondering, how do I tie all these lessons together, we've tried to kind of build that out. Our education team is all ex-scientist, ex-teacher, so we really have a good feel for the standards that you need to hit and what kind of narratives we can build into our lessons so that you can kind of see some consecutive lessons play out in a really cool way for your kids. On slide 5, if you're looking just to read more, the news section, which is full of articles we call teachable moments, written for the lay person to kind of just get a feel for what's happening in the world of NASA and space exploration. So these are constantly updated with whatever big breaking news is taking place, and our team is making sure that this kind of stays fresh and updated so that you guys can follow along. On slide 6, you'll see, again, a little bit of a screenshot of this teach section. And I come back to it because I want to highlight that whether it's today talking about engineering and communication across the solar system, or our previous talks that have been on Mars, you'll see these drop-down menus where you can actually, pull up the grade level that you're looking for, specific topics. There's a search function, so you can say, I really just want to learn about the moon today, or comets, or building rovers. So it's very, very easy to navigate. If you're a teacher, all of these are lesson planned in a pseudo 5E model. PDFs of assessments, of student worksheets, everything's already made for you. So it's really built to just kind of take off the shelf and run. On slide 7, you'll see the screenshot from that Learn section. It looks very familiar, but as I mentioned, it's a little bit more tailored to self-guided learning. And that's turned out to be really helpful these days because many of us in the education community are working in remote instruction. So if you are in a distance learning environment, this allows you to kind of send out cool activities to kids so they can kind of perform it on their own and then come back to your digital classroom and share their work. So these are a lot more self-authored, kind of driven by the student type activities. On slide 8, you'll see that the Learning Space website is kind of our attempt to make a nice one-stop shop. So if even this is too much for you to navigate, you'll enjoy being able to run through kind of some more themed and packaged activities, whether it's, again, something to do with your students, a video to watch, an assignment to create. We're working tirelessly because we know, it's tough for teachers out there. So designing new activities, we're making sure that our lessons get translated into Spanish. Both the videos have subtitles, and our worksheets are translated as well. And then, of course, just for you guys at home, we have just little FAQs for what it is that NASA does, what cool things we're trying to share, so that you can get involved as well. And then lastly, I'll just point out that, really this is just scratching the surface. There's so many more resources out there. I want to remind you guys that we have workshops just for the education community as well. So this coming Saturday, always the Wednesday is our technical talk. The Saturday following, we'll kind of run through and actually model some of these resources for you. So if you are a teacher or if you're homeschooling, we can kind of practice some of these together based on what we heard Bernardo speak about today. So hopefully that provides some continuity, and of interest to you, you can register in the exact same place where you found this webinar today. So with that, I'll probably wrap up. I hope that today worked well. The fact that we're still here and I'm speaking to a camera suggests that Lyle Tavernier is absolutely a tech wizard. So if you see him in the streets, make sure to wave and say hello. And thank you to everyone for continuing to dial in and make these events so fun and submitting your questions. I hope you enjoyed, and really look forward to hearing more next month, where we'll be actually talking about astronomy and some of kind of our how we still use light, a very similar theme, but how we use that light to explore the solar system. So make sure to check the website, tune in next time, and looking forward to seeing you guys again soon.